Dopamine is a neurotransmitter molecule that plays a role in controlling movement, learning, cognition, memory, and emotion. Dopamine regulation is an important part of many mental illness pathologies. A lack of dopamine is associated with conditions like anxiety, depression, and Parkinson's disease. Conversely, a buildup of dopamine leads to euphoric effects felt by recreational drug users. The dopamine transporter protein, also known as DAT, is partially responsible for regulating dopamine levels through the reuptake of dopamine in neuronal cells. Dopamine molecules, shown here in purple, are generated in the presynaptic neuron and transported into the synaptic cleft. Some free dopamine molecules bind to postsynaptic dopamine receptors and are carried into the postsynaptic neuron. Unbound, excess dopamine is transported back into the presynaptic neuron via the dopamine transporter. Dopamine is transported from the relatively low concentration synaptic cleft to the relatively high concentration presynaptic neuron. This is an energetically expensive process because the dopamine molecules must be transported against their concentration gradient. Rather than using energy from ATP to power this active transport, DAT takes advantage of secondary active transport, also known as ion-coupled transport. The cotransport of one chloride ion and two sodium ions provides the energy to transport dopamine. This is visualized in this figure. The red circles are sodium ions, and the purple circles are dopamine molecules. The sodium and chloride move along their concentration gradient from high to low concentration, allowing the dopamine to move against its concentration gradient from low to high concentration by making the net reaction energetically favorable. There are 4 binding sites that participate in the transport of DAT. 2 sodium binding sites, sodium 1 and sodium 2, 1 chloride binding site, chloride, and 1 substrate binding site, substrate 1. All are relatively close to one another in the molecule, located about halfway between the intracellular and extracellular regions. The steps of dopamine transport by DAT proceed as follows. The transporter begins in its outward-facing conformation, that is, open to the extracellular region. Sodium and chloride ions diffuse from the extracellular region into the molecule and bind inside sodium 1, sodium 2, and chloride. Dopamine also diffuses into the molecule and binds in substrate binding site, substrate 1. When the dopamine binds, the hydrogen bonding network is disrupted, which allows salt bridges to form that close the extracellular gate, keeping the dopamine inside the binding pocket. Simultaneously, 2 of the transmembrane regions begin to tilt inward. Momentary dislocations of the sodium 2 ion disrupt the hydrogen bonding network enough to allow water molecules to permeate from the intracellular region into the binding sites. These waters destabilize the substrate 1 binding site and cause the molecule to globally transition to the inward-facing conformation. In the reorientation, the sodium 1 and chloride binding pockets are enlarged, facilitating the release of these ions. Further, the protonation of amino acids in the substrate 1 binding site decreases the strength of this site's affinity for dopamine in the site, releasing dopamine also into the intracellular environment. Sodium 2 is not released. With no substrate bound, the extracellular gate reopens, and the transmembrane regions tilt again towards the outward-facing conformation. This entire process takes about 1 microsecond to complete. As is evident in the mechanism, the dynamics of the sodium binding sites are integral in the overall transport process. In both binding sites, the charge of sodium is 1+, the only biologically relevant oxidation state. Because the sodium is not a transition metal, the ions have no d-valence electrons, and thus primarily interact with the ligands through electrostatic interactions. Further, the ligand field stabilization energy of sodium-1 is 0 in any geometry. Because the LFSE is the same across all geometries, it does not help in predicting the binding site geometry. The sodium-1 binding site is 6-coordinate, which is a relatively high coordination number, so sterics likely prevent further ligand binding. While sterics are relevant, the protein folding is likely the driving force behind the geometry of the sodium-1 binding site. In the sodium-2 binding site, the metal ion is also bound to 5 amino acid ligands, but the water present is in the secondary coordination sphere. Again, for sodium-2, as with sodium-1, protein folding is the dominating factor to select sodium binding site geometry because it has a 0 LFSE and high coordination number. DAT must selectively bind sodium in a sodium and potassium-rich extracellular environment. Potassium and sodium are both alkali metals, so they have the same number of valence electrons and fairly similar electronic properties. They are both hard acids because they are not easily polarizable and tend towards ionic interactions. They prefer to interact with hard bases according to hard-soft acid-base theory, like oxygen, so they tend to coordinate the same ligands. But the potassium ion has a larger ionic radius than the sodium ion. Because of this, the potassium ion is too big for the sodium binding pocket. Hence, ionic size allows DAT to select for sodium. A labile coordination complex is one in which ligands are exchanged very quickly. In contrast, an inert compound is not labile and exchanges ligands slowly. The lability of a compound can be predicted using Taube's rules by the strength of its ionic interactions and the d electron configuration. The stronger the ionic interaction an ion has based on Coulomb's law, which says that small, highly charged molecules have stronger interactions, the less labile it is. The sodium an ion in my system has a small charge of 1+, making it fairly labile. This ion does not have any d electrons, which makes it very labile according to Taube's rules. Both evidence from the d electron count and the Coulombic interactions indicate that sodium-1 is labile. Also recall that the LFSE for sodium-1 is 0. 0 is the largest possible LFSE value for an octahedral complex because all other values are negative. The more negative an ion's LFSE, the more stable that complex is. Therefore, this large LFSE indicates that sodium-1 is thermodynamically unstable. Thermodynamic stability informs chemical lability. It follows the trend that, generally, thermodynamically unstable compounds based on LFSE are labile. DAT can transport dopamine at a rate of roughly 1 million molecules per second, so the lability of sodium is good for the DAT system. If the metal weren't labile, it would not release easily from the transporter, slowing down the overall transport process of dopamine. DAT and related neurotransmitter transporters are the targets of many drugs used to treat depression, ADHD, anxiety, Parkinson's disease, and other neurological disorders. These drugs block reuptake of dopamine, that is, they inhibit the function of DAT, increasing the amount of dopamine in the synaptic cleft. It is also known that DAT is linked to drugs of abuse. For example, cocaine binds to DAT with high affinity, resulting in a high level of extracellular dopamine, which contributes to the euphoria that cocaine users experience. Understanding how DAT works, particularly how it interacts with pharmaceuticals and recreational drugs, will lead to new approaches to treating prevalent psychological disorders, hopefully resulting in better patient health.